Google Meet.
Oh, okay.
Let me try a different headphone. I'm trying different headphone. Hello?
Yes, sir.
Can you hear me?
Yeah.
Yes.
Yeah, I think the noise is also reduced.
I think this it's still echo is there, but I think this is little better.
Yeah.
Okay. So should we start? Should we start?
Yeah, sure. From
Okay.
me.
So before we start, I just want to remind you all some few things. Just like kindly turn off your microphone when you are not talking, and if you have any question while the talk is going on, you can put it in the chat box, and wait for your host to communicate further. Today we are very excited because the speaker we have with us is the one name we had from very beginning when we planned for this lecture series. So the formal introduction will be done by our host Shreya today. So I hope you all will enjoy this seminar, and thank you. Shreya.
Thank you, Kuchita. So once again, welcome you all to the 5th lecture of the Nature as We Unfold It seminar series of CAPSS. I am glad to introduce our today's speaker, Professor Ajit Mohan Srivastava. Professor Srivastava is a senior professor at Institute of Physics at Bhubaneswar, Orissa. He has varied research interests ranging from condensed matter experiments to cosmology, to quark-gluon plasma, to gravitational waves. His first publication came in the year 1981 when he was doing his bachelor's at Allahabad University. He then moved to IIT Kanpur for his master's and finished his PhD from Syracuse University, USA. He joined Institute of Physics, Bhubaneswar in 1994 and was its director in the year 2013 to 14. He has his own liquid crystal experiment lab to study topological defects in nematic liquid crystals and their implications for cosmological evolution, with publications in journals like Science and PRL. With his students, he was the first to use the idea of super horizon fluctuations in CMBR to predict similar features in relativistic heavy ion collision experiments. Another interdisciplinary work involves the use of pulsar timings to infer a possible QCD transition in the core of a star. Today he will talk about how pulsars can act as detectors for gravitational waves. He is very active in outreach program of the institute as well. He has regularly organized stargazing sessions in and around IOP, open physics discussion for school students as well. He is the vice president of Samantha Chandrasekhar Amateur Astronomy Association and has been actively involved in popularization of astronomy. So I welcome the speaker, and sir, now you can have the mic and you may start now.
Okay, thank you. Let me share the screen. Visible to everybody?
Yes,
You
sir.
can-
Yes, sir.
Okay.
It's visible.
Okay, thank you very much for a very sweet introduction, very nice detailed introduction. And this is indeed my pleasure to be giving talk at your forum. I have visited your place so many times and I have very good memories of that, very good discussions. And so, as you have told me, that the idea is to actually discuss, make this, have this physics discussion talk, and also sort of extend the discussion towards the way I do research. I mean, different, what are my views of what different ways of doing research, like interdisciplinary research versus specialized research and all that. So actually, the topics I gave you, this topic and the other topic, they are sort of capture the essence of the way I do physics. So I thought these will be good topics. So this is a topic of that kind. So when I discuss this topic, I'll also start telling you how we went along, how this problem evolved. It evolved from very different thing. I had never worked on gravitational waves, never at all. this was not even my horizon to work on gravitational waves. My work on quark gluon plasma was what we were discussing, and how we ended up in gravitational waves and all that. So I would like to mention that also in detail. So let us start. Gravitational wave astronomy is by now a new upcoming thing. Everybody knows, with LIGO and Virgo detecting black hole collisions and neutron star collisions. It has become now very important to realize that the gravitational wave signals which will be coming have a very different kind of forms depending on the source. For example, the binary pulsar will have periodic waves. If you have a supernova or GRBs, then there will be a spike like in middle, and then there are collisions. These are binary collisions. These are the kind of things with LIGO and Virgo have detected. And of course, most interesting thing will be eventually noise is very important. Noise is the most important thing. This is how cosmic microwave background radiation was detected. When they could not remove this background noise, Penzias and Wilson, they kept at it, and eventually it was recognized to be CMBR. So there will be a stochastic background of gravitational waves that will be coming from the earliest time of the universe, literally from the beginning of inflation. So that will be the most exciting, but that's very far away right now in terms of direct detection. Important thing to recognize in all these things is the waveform is very important. In all the methods of gravitational wave detection, you need to know waveform in advance, because the noise reduction techniques and different techniques, they require what kind of signal you are looking for. Even in the signal we have proposed for pulsars, this is very important. This is called template. You have a template of the original signal, and that plays extremely important role in noise reduction thing, because you have a huge amount of noise compared to the signal, even in LIGO Virgo, and how you get signal to noise ratio to manageable level. So let's start with the pulsars. Pulsars are rapidly rotating neutron stars. Many have been detected with radio telescopes. The CAPSS pulsar, for example, also in the optical region. They have wide range of rotation frequencies from 1 Hz to kilohertz. The important thing is that they are extremely accurate observations of pulsar timing. This is will be focusing, and I'll mention many things about it. So pulsar is a rotating neutron star. Radiation is emitted from magnetic poles, which are misaligned from the rotation axis. So because they are misaligned, so there is a rapidly changing electric field, which excites the electrons, and electrons get accelerated and radiation is emitted. So the radiation is emitted along the magnetic pole direction, and rotation axis is different. So whenever this, it's like a flashlight rotating about a different axis. So whenever it, and people call it like a lighthouse beacon. So whenever it points towards you, if it intersects Earth, then you see a periodic pulse, and that's called pulsar. First detection of gravitational wave was through pulsars. I guess many of you would know about that. In the 70s, Hulse and Taylor, they observed their binary pulsar system, which consists of 2 neutron stars in close proximity. They radiated energy such that its period decreased by 75 milliseconds every year. Imagine 75 milliseconds every year. They were able to detect it. That's the pulsar accuracy. So it's a kind of crowded slide, but you don't need to worry too much about it. Basically, it is, you can see my cursor pointer here. Hello?
Yes, sir. Yes, sir.
You guys see my cursor pointer here?
Yeah.
Okay, good. So this is the binary pulsar system. This is the 8-hour orbit time and 17 rotations per second is the pulsar timing in this case. And energy of this system, gravitational energy, is minus gm1m2 by 2a. A is the semi-major axis. And so as the gravitational wave is emitted, there is a changing quadrupole moment here. So gravitational waves are emitted. And as energy is emitted out, the energy will decrease. And this energy, gravitational binding energy, is negative. So energy decreasing means A must decrease. So A decreases, so the objects come closer to each other, and eventually these objects coalesce. That's what happens. That's the kind of coalescence of black holes or coalescence of orbiting neutron stars has been detected by LIGO and Virgo. But here it's different. Here they are just coming a little closer, and that orbit change has been detected. It is a spiral in. It's amazing. GTR prediction is spiral in by 3 millimeters per orbit. 3 millimeters per orbit. And imagine they are separated by a million kilometer, and the change is 3 millimeters per orbit, and this is the data. The solid curve is the theoretical prediction of gravitational wave emission, and this is the data and amazing accuracy. So this is they're able to do because pulsars are extremely accurately measured. And this had shown, this was of course indirect detection of gravitational waves. Nobel Prize was given in 1993 for that. I want to tell you about these things also because you should know pulsar has been very instrumental towards search for gravitational waves. Our methods are completely different, so it's also important for you to know what methods have been existing so far. So I told you about Hurst-Taylor binary pulsar. Now there is a very important technique called pulsar timing array, PTA. This is a method which is supposed to detect gravitational waves for extraordinarily low frequencies. This is a 10 to the minus 6 hertz. 10 to the minus 6 hertz. So there is extremely long wavelength gravitational waves. And what one does is that one chooses the most accurately measured millisecond pulsars, and their timing accuracy for 10 years is comparable to that of world's best atomic clocks. So what you do is that you measure the pulses coming from that different pulsars, and if the gravitational wave of long wavelength passes through in between, the timings of different pulsars will get modulated, and in a very coherent manner. That's the important thing. So you measure those minute changes and you say there was a gravitational wave. So for example, you have if all pulsars have the same time of arrival variations, it will be a monopole signature, it will be called clock error. If they're coming from the orbit, solar system orbits, then it will be dipole signature, and you are looking for quadrupole signature. Means the pulsars around Earth will show a quadrupolar changes in time shift. That will be of course no detection has been done so far for this, but this is a very ambitious plan. It has been going on for a long time. So now what I want to tell you is a completely new possibilities with pulsar. And as I said, I will tell you how we went about detecting evolution of this method. So pulsar observations are extremely accurate measurements of pulsar timings, highly sensitive to structure of neutron star. And this was our first work, which we started by looking for density fluctuations during phase transitions in the pulsar core. And the imprints on pulsar rotation dynamics, it was because of changes in moment of inertia and quadrupole moment changes. And this was done with my ex-students, Partho Bagchi, Arpan Das, and Vlaik. So in that, of course, the observational implications were changes in pulsar timings, and they were gravitational waves. This is where we entered into gravitational wave search. So first I'll discuss that, and then we will discuss about the extreme sensitivity of pulsars to external gravitational waves. And I'll tell you how pulsars can act as remotely stationed Weber gravitational wave detectors. It's a new kind of detector which we are proposing. So it's sensitive to different kind of binary mass ranges, and one has exciting possibilities of even having primordial black hole within the range of detection. And then the most exciting part, toward the end, I will tell you is it opens up a new possibility of revisiting past gravitational wave events. That will be the last part. This is the work which we have just published, Miniti, Shreyansh, and myself. So let us start discussing with neutron stars. Neutron stars typically form in supernova explosions. Mass of the order of 1 to 2 solar masses, can go up to maximum 3, something like that. Radius about 10 kilometers. And central density as high as 5 to 10 times the nuclear density. Equilibrium density is very high, 10 per 14 grams per centimeter cube. And they have initial temperature of, when they are formed in supernova explosion, very high temperature, 10 to 30 MeV. And they rapidly cool to about 0.1 MeV within minutes, and then keeps cooling further down. Cooling happens by neutrino emission, and subsequently there is slow cooling. A neutron star is the densest form of matter in the observable universe, and pulsars are rapidly rotating neutron stars. kindly just hold on for a minute. I need to hold on my talk.
Yes, sir.
Please hold on just a minute. Okay, my apologies. Let's begin with again. Hello? Hello, everybody
Yes, sir.
there?
Yes, sir. Yes.
My apologies. I had to. Okay.
It's okay.
So, so this is the structure of neutron star. It has a very dense core, and one doesn't really know what happens in the core. The exotic possibilities, and actually this is where our interest began in neutron star. I'll tell you about that. Its size can be 1 kilometer or a few kilometers, and it has a very exciting possibility of QCD phases, coagulum plasma, and even more exciting phases at high baryon density. Some of you who know about the QCD phases at high baryon density, there's a color flavor lock phase, and there's a 2SC phase, and all those. And this is what we were interested in, and so we were interested in, and this is the only possibility. Other possibility is these heavy ion collisions at low energies, which are being carried out at FAIR, NICA, and the beam energy scan program of RIC. So it's very important to realize that neutron star is a very exotic object. In fact, when I learned about neutron star, I was amazed. We in high energy physics, we talk about very exotic things like cosmic strings and the wind walls. And the neutron star is a very, it's an astrophysical object, sort of mundane. I would thought, okay, fine, it is a very dense object. Its structure inside is phenomenal. I mean, it is supposed to have a neutron star superfluid inside. It's a very high baryon density object, so, and at a cold temperature, relatively low temperature, neutrons form Cooper pairs. Neutrons near the Fermi surface, they form Cooper pairs, and they condense just like in superconductivity. Of course, they are neutral objects, so you got superfluidity in this case. And the rotating objects, so these rotating superfluid form superfluid vortices. So there is a whole network of superfluid vortices. So you will think, okay, fine. So what's the big deal? A big deal is this: these superfluid vortices are the only way you can explain some of the really interesting observations of neutron star, and the properties of these vortices are amazing. I find the thickness is few Fermi. Thickness of these vortices, because it's QCD, neutron star, neutrons pairing up. So the thickness of these vortices is few Fermi, and they are stretching along the rotation axis through several kilometers straight. Okay, and how far apart the bundle is, they are a few millimeters to centimeter apart each other. So you have a several kilometers cross section of vortices, a few millimeters, centimeter apart, stretching to several kilometers straight, and thickness being a few Fermi. This structure is, I think, really very exotic, and we should think about it. So, and this is very important. Okay, let me skip that one. Yeah. So what happens? These vortices, which are in superfluid part, they are pinned at the interface. So there is a vortex lattice, and these vortices are pinned at the interface with crust. Now what happens is that neutron star is rotating, and it slows down eventually. It keeps slowing down a little bit, and the vortice system gets strained. And because of the strain, this is the detachment of vortices, periodic detachment. So, and when they detach in bunches, and the moment they detach, they go out, they get absorbed in the shell which is rotating, and it suddenly increases their rotation. So neutron star outer surface which is rotating, it suddenly gets a jump in the rotation. This is the phenomena. This is the explanation. This is all theory I'm telling you. This is the phenomena. This is the explanation offered for a phenomena of what's called glitch. So the glitch is sudden increase in rotational frequency and then very slow relaxation over several months. So delta nu over nu, rotation frequency, delta nu over nu changes by 10 to the minus 10 to the minus 9. It's an incredibly small change. But it does change that much. But a very rapid change. And it slows down, it relaxes by a very slow amount. So for explanation of this, people have proposed different things like crust quakes, etc. But the most satisfactory explanation is in terms of angular momentum, transverse angular momentum due to deepening of clusters for superfluid vortices, as I told you. Important thing is, recently there are observations of anti-glitches, suddenly slowing down of rotation. Now, if you think about this mechanism I just told you about vortices deepening and suddenly getting absorbed outside, it can increase the angular momentum, but you can't decrease the angular momentum this way. So the deepening of vortices, which was the sort of universal explanation for glitches, doesn't work for anti-glitches at all. So anti-glitches, people invoke something fell on the neutron star, or there was some star quake or some random phenomena like that. So what you will see is that when we will propose our explanation for glitches, you'll see that glitches, anti-glitches get unified. In fact, you have a uniform explanation for those. So pulsars are incredibly accurate clocks. I have been telling how incredibly accurate they are. This is the period of the first discovered millisecond pulsar. This is accurate down to the last digit. This is slowing down at a rate of 10 to the minus 19 seconds per second. So this pulsar, for example, the error is 10 to the minus 17 seconds in this case. This is the accuracy of 1 part in 10 to the 15. 1 part in 10 to the 15. It's a phenomenal accuracy. So when we came to know, when we learned about this thing, we got very excited. Okay, the pulsars are very accurate, really measured object, and their center is a neutron star ultimately. So its center is very exotic place where you can have these phases of QCD. So how do we use this? So this was our first. So the whole actually idea was in this case that we should look for the exotic phases of QCD, CFL, etc., or even nuclear superfluidity, how to look for these things. And when we looked at the literature, so I mean, let's look at it. So we were learning about CFL phase and all that, and then you want to know how to observe it. So of course, heavy ion collision is one possibility, but we all know it's very difficult there to reach such kind of baryon density. One is hoping, but very difficult. One almost very likely places are the cores of neutron star. And people have done a lot of work on that. There are a lot of papers you will find that how to detect CFL phase and 2SC phase, etc. What are the observational signatures? So we looked at those papers, and what we realized is that they are very model dependent. It really depends on what is the energy gap in this case for superfluid state, and what are the specific modes of excitations and all those things. You change those things, and things like cooling rate, etc., all those things change quite a lot. That obviously is not a very satisfactory situation. So what we wanted to do is to see if we can propose signals which are reasonably model independent signals. And there the help came from the fact that I have been working on this topological defects for a long time. And one thing which I have been doing is to do liquid crystal experiments where you measure topological defects in liquid crystal system, and you actually check theories of cosmological defects like cosmic strings and all that. The reason you are able to do it is because a defect being topological in nature, they have universal features. So universal features simply means there is no model dependent at all. They depend on very robust properties like topology, symmetry, space-time dimension, and things like that. So when with that kind of background which I have from my work, it became very immediate that the way to look for these exotic phases in pulsars would be to see if there are topological defects. Topological defects invariably form in phase transition. So idea is to look for phase transition, and phase transition necessarily produce density fluctuation, and density fluctuation will have universal property, may have universal property. If they have, then you are avoiding all the model dependence. That was the whole soul. So right now, this is our first work. This is with Partho, Arpan, and Beshuna. So now, what happens if you have a first order transition, then proceeding by bubble nucleation, then random bubble nucleation will lead to density fluctuation, and you will know typical density scale, distance scale would be inter-bubble separation. And if it's a second order transition or smooth crossover, then we know, well, for second order transition, we know that there will be critical regime. There will be universal regime, actually. There will be universal nature of density fluctuations. And even in smooth crossover, there will be density fluctuation of different kind. So if you have whether you have any kind of transition, even crossover, if there is a symmetry breaking, then there may be topological effects, spontaneous symmetry breaking. And all these QCD phases have a spontaneous symmetry breaking, and all of them have associated topological defects with them. That's what we realize. So this topological defects will be produced, and topological defects are, of course, defect because the free energy is different inside topological defect. That means there is energy density fluctuation. In fact, that's the reason cosmic strings were first proposed for structure formation, because there is a lot of energy density in them. So the idea is clear that you have a phase transition and topological defects are produced. You look for density fluctuation. So what happens to density fluctuation? Now, if there is a density fluctuation, so imagine you have a neutron star which is a spherical object. So for simplicity, you take a spherical, rotating with high angular speed, very accurately measured. And there is a random, there is a phase transition because of which there is a random density fluctuation inside. If there is a random density fluctuation inside, its moment of inertia will change, and so will its quadrupole moment. So the idea was that, so we realized that if there is a random change in moment of inertia, then you should be able to see it in the change in the pulsar timings. And pulsar timings, as we know, are very accurately measured. So if they, of course, the density fluctuations are random. Random means that if they change moment of inertia tensor, it will be completely general change. Moment of inertia tensor which will have a completely random changes. So if there is a change in diagonal component of moment of inertia, this will result in, of course, rapid changes in rotation of pulsar. And as density fluctuation will dissipate away, it will lead to uniform new phase. Some part of change in moment of inertia will be restored, but not fully. So what this means is that the rotation rate will change suddenly, but it won't get restored completely. You realize this was exactly the nature of glitches I had told. And as you see that because there are random fluctuations, the moment of inertia diagonal component may increase or may decrease. They are random. So that means you may have a rotation increasing, speed increasing, or rotation speed decreasing. So glitches, anti-glitches, both can be explained in this equally by the same method. Now, interesting thing is that in our case, moment of inertia changes by a random amount. So off-diagonal components of moment of inertia will be necessarily produced. What will off-diagonal components of moment of inertia will do? They will induce wobbling. Because rotation axis was something, now your principal axis of rotation would become different because they are off-diagonal components of moment of inertia. So the start will wobble. Wobbling means that it's not just the rotation speed which is changing. The pulse which was pointing at certain angle to you, that angle is changing periodically now. That means pulse profile will also change. This became a distinctive signal for our method. Because you see, when you see things like conventional method of deepening of vortices are all aligned along the rotation axis. So when they deepen, rotation changes. There is no off-diagonal change, rotation change in the moment of inertia there. Apart from some fact that if the vortices change in asymmetric manner, there will be some minute amount of change of diagonal component. But dominant change in rotation is because the angular momentum getting transformed from well-aligned vortices aligned on rotation axis. So the off-diagonal component will be very, very negligible in this case. So the wobbling will not be introduced much. Whereas in our case, wobbling will be of similar magnitude as the spin rate change. So this is a very distinctive signal which we have proposed, which can separate out this method versus other. These are some of the simulations we have done in which we found that it was very difficult to do simulation in this case for field theory simulation, because you're talking about 10-kilometer object where field theory is working at the level of Fermi. So you have to try to extrapolate by considering different sizes. To some level we were able to do it, but for first order transition our numbers were reasonably fine. And what we proposed is the value of delta I over I might range from 10 to the minus 14 to the minus 10. This is an incredibly small change, 10 to the minus 14 to the minus 10. But important thing is, if delta I by I changes by 10 to the minus 14 to the minus 10, that is the change in rotation frequency, 10 to the minus 14 to the minus 10. And that, as you can realize, is very well within the range of accuracy of measurement of pulse timing, which are measured to 1 part in 10 per 15. So what we said is that this is within the range of observation. Now this is where we enter in gravitational wave. So far it is all about QCD. Then we realize that it's not just rotation which is changing, rotation speed. There is a change in moment of inertia. It's a random density fluctuation. There is necessarily a quadrupole moment also changing. So is there a quadrupole moment changing? Of course, it amount seems very small, 10 to the minus 14, 10 to the minus 10. So you may think gravitational power will be negligible, but just hold on for a minute. Gravitational wave power is q triple dot square. Q triple dot square. Third time derivative. So that means even if delta q is small, is delta t comes with the power cube in the denominator. So if that is very small, it can compensate for q to be very small. So the fastest time scale for conventional mechanism of gravitational wave emission is millisecond, and with q by e of order 1000. So, so you see, this is what people have been discussing, that if there are changes in neutron star properties, like say a star quake or something, gravitational wave will be emitted. There people talk about changes in quadrupole moment to inertia of the order of 10 to the minus 3. We are talking about q by I of order 10 to the minus 10. But time scale is at most microsecond. So you see, time scale being microsecond, whereas time scale for the other case was millisecond. So there is a 10 to the minus 3 benefit in this case in time scale, and you cube that to 10 to the minus 9 benefit in the gravitational power. So the basically idea is that because of very short time scale, the gravitational power can be very large. This is the expression for this power delta. This is this. So d by dt is the power, and delta q by r naught to 10 to the minus 6 and to square. And this is the real thing. So rest are you forget about. So delta q over I naught. Delta q over I naught of 10 to the minus 6 is the conventional wave, delta q I naught, and our delta q is 10 to the minus 10, delta q over I. So you lose here. But delta t is, in our case, at most 10 to the minus 6. It's generally much smaller than that. And there is a power 6 here. There is a 6 here. Sorry. d by dt. So, so that will lead to huge benefit. So basically, you have a very bright source of gravitational wave from these phase transitions, which are governed by QCD time scale. You see, I mean, the underlying time scale is QCD. That should be in Fermi's, but ultimately the density fluctuation should become macroscopic. So the largest time scale which we could come up with was a microsecond in this case, coming from the first order transition. That we see. And I had given this talk in front of a LIGO group there in Syracuse University, and they were interested, and they were asking. So they told me actually that the LIGO is presently tuned to kilohertz regime, but it can be tuned to megahertz regime. They have not tuned it, but they can turn to megahertz regime if they believe that there is a source, clear source. So our proposal is that megahertz frequency is a very important source of gravitational wave coming from phase transitions like neutron stars. So that was our first work, and now you see, now we have entered gravitational wave. So QCD is sort of become secondary, and then once we are thinking about gravitational waves, so far we talked about gravitational waves being produced by the neutron star itself. But you see, really the main thing was that the phase transition was making very minute changes in the neutron star structure, and you were detecting that by the pulse timing, the change in the pulse timing, because the rotation rate would change. Then obviously natural question was, if there is a pulsar sitting and a gravitational wave strikes it, then what will happen? Pulsar would deform. would that deform sufficiently that you can detect? If pulsar deforms, its rotation will change again. That's what we talked about. In earlier case, it was random changes in density because of phase transition. Now it will undergo quadrupolar deformation by external gravitational wave. So will this affect the pulse timing significantly? You can detect it, and this may be unbelievable. I mean, you would think, how is it possible? Because you all have heard that how incredibly tiny the deformations are. H, the amplitude of the gravitational strain, which is called delta x over x, is 10 to the minus 20. 10 to the minus 20. So, with such a small gravitational strain, how can you ever try to detect this change? Then it is important to know about Weber gravitational wave detector. So I'll tell you, in this picture, I'll tell you about Weber gravitational wave detector. So what we will discuss is that now there is external gravitational wave coming and there is a pulsar. Pulsar will undergo a quadrupolar deformation, and quadrupolar deformation will induce very tiny changes in its pulse timing. And can we detect it? Important thing will be, in this case, this effect will be most pronounced at resonance. Resonance would mean that the gravitational wave frequency is similar to the some natural frequency of neutron star, vibration, oscillation, thing. Some normal mode of neutron star. If that is there, then the neutron star will absorb the signal energy to a maximum possible amount, and that is the important thing. In fact, we'll tell you that the main part of our work is that what we have demonstrated is that resonance is actually likely in this case because a pulsar equation of a state and something called tidal deformability, they have been constrained by recent BNS merger. You know that LIGO and Virgo have detected many collisions of black holes. They also have detected a couple of neutron star collisions, neutron star coalescence. Through that analysis of signal, they have measured, put constraint on a very important property of neutron star, which is called tidal deformability. That is the value which we use, the constraint value. So, if that works, if this proposal works, then the pulsar will become your remotely stationed Weber detector of gravitational wave whose signal can be monitored on Earth. And I'll try to give you this picture in detail. So first, what is a Weber detector? This was the first gravitational wave detector ever proposed by Weber. This is Weber's picture, and this was his bar detector. Bar, and the bar will resonate. So it's supposed to be It's supposed to work at resonance. So the bar was chosen such that the expected signals were known, primarily coalescence of black holes, coalescence of neutron stars, and all that. So frequency was expected to be 100 hertz to kilohertz. In that frequency, this was supposed to work. Several of kilohertz frequency. It was supposed to be natural frequency of vibration of the bar, and the deformation of this bar was supposed to be detected by piezo crystals as shape deformations, and they were supposed to detect this signal. So you see, what's happening here is that gravitational wave comes and strikes this bar. So of course, originally there was this bar. Now people have these fears because bar is most sensitive towards waves coming from its perpendicular direction. Sphere, of course, can detect waves coming from all directions. Principle remains the same. So, so the gravitational wave comes and strikes this Weber detector, and they start vibrating. The piezo crystals lead to the pulse of signals which come, and you observe the electrical pulse. What is our proposal is the following. This is the pulsar rotating about this rotation axis. This gets the gravitational wave comes and strikes the pulsar. It undergoes a deformation. Tiny deformation indeed. What changes here? There is no piezo crystal there. What changes there? Its rotation frequency changes. How do we get that signal? Because we are measuring its pulsar timing very accurately. 1 part in 10 power 15. This is accuracy probably even better than the electrical currents are measured for Weber case. Weber currents are measured with very great accuracy as from piezo crystal, and so are these pulses. So the difference is that the Weber detector sits in the lab connected by wires to your monitor and computer. Pulsar is sitting out there just like a Weber detector, and the signal is coming through the pulses which you're already detecting by radio telescope on Earth. The fidelity of these signals is phenomenal in both cases. That's the important part. So that's our proposal. So your pulsar works as a Weber detector. So this is the thing. So this is the gravitational wave coming. You must have seen these kind of pictures. They represent quadrupole deformation, and the pulsar you take it to be a spherical pulsar with mass m, radius r. Gravitational wave coming, strikes it. So this is the sphere that undergoes quadrupolar deformation, and these are the equations which people use for the neutron star case. That the quadrupole moment induced by gravitational wave. So when there is a gravitational wave, then there is a tidal deformation, and there is a tidal field. There is a tidal field of gravitational wave, which is Eij. I'll tell you what it is in terms of gravitational wave strain. And induced quadrupole moment is simply given by minus, is a proportionally constant, minus lambda d times a. Lambda d is the tidal deformability. This captures the entire physics of neutron star. So you are simply telling that there is a gravitational wave coming with has some tidal field given by some gravitational strain. How much will star deform? Naturally, it depends on the properties of neutron star. It depends on the stiffness of the equation of state and those kind of things. So this lambda d is actually tidal deformability is again written in terms of other parameters, radius of the star, and the g is a gravitational constant. And in terms, and this k2 is the number which is called a second love number. And this number is a dimensionless number, and this number captures the essence of the properties of neutron star. And for neutron star, its value is 0.05 to 0.15 as constrained by the recent BNS merger of gravitational wave. So this is the tidal deformability. If there is a gravitational wave coming, it has you will have a Riemann curvature tensor will be given. So tidal deformability are Eij. Sorry, this tidal field of gravitational wave is Eij, is Ri0J0, and the Riemann tensor can be written in terms of this, where this is the h mu nu t. This is in a specific gauge called transfer stress. This is you don't need to worry about this. This is just some equations. And eventually you write this h mu t in terms of this tensor, which tells you two polarization modes. You must have heard about gravitational strain H, and that's what I'm coming to. So let's take one polarization mode with H plus mode, and you put that H plus C mu nu as H plus this thing here in the matrix, and from that you calculate Eij. So Eij you can calculate, so Exs, Eyy you can calculate from that. This is the tidal field of the gravitational wave. And you write all those things because the second time derivative, the wavelength will come. So 2 pi square hc square by lambda square, h is the gravitational strain, which is in this case we are taking the plus polarization, for example. So resulting change in the quadrupole moment tensor will be Qij minus lambda d Eij. I told you Eij is given by this expression. So you can write finally that the change in moment of So what we have got here quadrupole moment change, right? Qij. But we took a very specific model of quadrupole moment. We said you take a sphere and consider its quadrupole moment by a quadrupolar deformation. We now, if you assume that quadrupolar deformation given by this quadrupole moment, you can calculate the change in moment of inertia also for that geometry. So we calculate change in moment of inertia, and what you find is delta I xs over I is minus delta I yy over I is given by this expression. So we put in all the values for typical neutron star, mass similar to sun, radius 10 kilometer, and the typical frequency which is in kilohertz frequency, and second love number is 0.1. So what you find is that delta I xs over I is 10 to the minus 2 times h. So now imagine, so maybe let me just go a little slow on that. What you are saying is a gravitational wave of strain h falls on a neutron star. Neutron star's moment of inertia will change, which is delta I xs over I, which will be 10 to the minus 2 times h. Now, LIGO Virgo detected the BNS merger event, which was a peak signal strength H of 10 to the minus 19 on Earth. So this was binary neutron star merger event, and this binary neutron star system was 130 million light years away from Earth. And the signal was 10 to the minus 19. The gravitational strain amplitude decreases at 1 by r. This is just like the amplitude for electromagnetic wave, but it goes at 1 by r. So, importance of our neutron star, our pulsar detector would be, of course, that it doesn't have to be on Earth. It can be anywhere. So it can be close to where neutron star merger happened. So suppose this, suppose there was a pulsar which was close to this BNS merger. Suppose only 100 light years away from that. So you see, 130 million light years, the signal is 10 to the minus 19. If 100 light years away, signal will be 10 to the minus 13. Gravitational strain. So if h is 10 to the minus 13, and you have this expression that delta I over I 10 to the minus 2 times h, you find that delta I over I, which is same as delta nu over nu, which is change in rotation frequency, will be 10 to the minus 15. Now you realize this is the thing which you are talking about. Delta nu over nu of 10 to the minus 15 is completely measurable on Earth. Completely measurable on Earth. We have been measuring pulsar pulse timings to that accuracy anyway. So this is, of course, if you are lucky and you happen to have a pulsar which is 100 light years away from the gravitational source. If it is 10,000 light years away, it will be 10 to the minus 17. December 10 to the minus 17. Now, 10 to the minus 17 may look tricky because we have, I said accuracy 10 to the minus 15, we have delta nu over nu. What about 10 to the minus 17? That's because we have not talked about, I have just said if there is a change like that, deformation, you directly see this change. The important thing is, very important thing, is something called ringing effect. The Weber detector it doesn't measure the signal directly. If you have a 10 to the minus 20 signal, h of 10 to the minus 20, that kind of accuracy is very hard to obtain from a Weber detector directly, because ultimately the piezo crystals, they are not that that sensitive. What happens is that in this manner, the Weber detector is fundamentally different from the LIGO. What happens is the gravitational wave comes and it moves the mirrors, and you have a signal. And the signal lasts exactly for that much duration as the gravitational wave passes. So if a gravitational wave passes for a millisecond, the signal lasts for a millisecond. So you have to measure during that time. Weber detector is fundamentally different. Weber detector is a solid detector. What happens is it's working at resonance. As you know, for a harmonic oscillator or an oscillator, damped oscillator, all the physical systems are damped, right? They have this equation. Damped oscillator working at resonance is very important, because when it works at resonance, it absorbs maximum energy from the driving force. Maximum energy. So what happens is, the gravitational wave, when it's coming and it strikes the Weber detector, solid bar, aluminum bar or copper bar, its energy is absorbed in the detector. So it vibrates, but it keeps vibrating. It's like a tuning fork. You take a tuning fork and you hit it, or just a bell, just a bell. You take a bell and you hit it by a hammer. The external driving force is the hammer. You hit it in a millisecond or something like that. But the bell keeps ringing for a long time. Why does it keep ringing? Because you're hitting the bell by a hammer has absorbed that much of elastic energy into the bell, and that with that excitation, it has absorbed that much energy, and it keeps ringing with the same frequency. Bell's frequency doesn't change. It keeps ringing with the same frequency. So it keeps ringing with them. So the same thing with Weber detector. Acting in resonance, when gravitational wave comes, a millisecond gravitational wave comes, it hits it, it absorbs the energy. So even if there is a millisecond wave hitting the Weber detector, it absorbs the energy. It keeps vibrating with that mode for minutes, in fact up to 10 minutes. And because it keeps vibrating exactly with same amplitude, with same kind of mode, like which is an oscillatory mode, you can fold the pulses. They call folding the pulse. Your same pulse again and again, millisecond pulse, but coming again and again for 10 minutes. So you fold it, and that enhances the signal to noise ratio tremendously. Important thing in this case is that energy should not dissipate too fast. Your Weber detector should have a what they call high quality factor. So, okay, let me first. So it should have high quality factor. Quality factor Q for oscillator, damped oscillator, is simply given by the total energy of a system initially divided by energy lost due to dissipation in one oscillation cycle. Okay, net energy of system divided by energy lost by dissipation in one cycle. So, for Weber detector, people use typically material which has a Q factor of 1 million or even more than that. That means that in each cycle, the energy loss is only 10 to the minus 6 fraction of the total energy. This Q factor then becomes very important. So that means it will keep oscillating for 1 million times more. 1 million times pulses it will keep oscillating. You can fold 1 million pulses. That much accuracy. So this thing is very important. So now what this means is now we are saying our Weber detector, pulsar being Weber detector. Pulsar absorbs this energy of gravitational wave and it will keep oscillating. But then it must keep oscillating for a long time. So we need to know what the Q factor of a neutron star interior. And we don't know. Nobody has paid attention to this factor. In fact, this is one of the main, I think, contribution of our work, that we have brought attention of the community to this factor, quality factor for neutron star. Quality factor depends on viscosity, etc. But many more things than that. So quality factor needs to be known. One only knows that viscous effects are not very dominant for the relevant time scale. That is done by observing the decay of orbits of in binary pulsars. So the people observed that for these relevant frequencies, dissipation is not very strong. But one doesn't really know Q factor. But I'll tell you later also, the Q factor is expected to be very large in this case. Million should be at least, it should be much more than that. And so, an important thing is neutron star resonant modes are all known. People have worked them out. So, and there's 100 hertz to 1 kilohertz or even 1 hertz, there are lots of resonant modes. The important thing is that the gravitational waves coming from coalescence of black holes and neutron stars is very, very likely that neutron star pulsar will be in the resonant mode with that and will show ringing effect. So again, I have just repeated here, a Q factor of order 10 to the power 6 was important for Weber detector. So this is very important for this Weber detector acting as resonance, and a gravitational wave pulse lasting a few milliseconds, the resonant bar can continue to ring for time order of 10 minutes, and it helps in improving signal to noise ratio. So we need to know the Q factor, I said, for neutron star interior, and this is the new challenge for QCD calculation. Apart from the well-known problem of determining the equation of state and viscosity, one should know what the Q factor of a neutron star interior. And it will be important, the most crucial thing for knowing whether the ringing effect, how dominant ringing effect is there. With all that, the proposal is the pulsars will become a family of remotely stationed Weber detectors. What we have argued is that pulsars spread out in space may act as gravitational wave detectors. Their pulse detected by pulsar observatories, which are radio telescopes, because the pulses of pulsar will carry the imprint of gravitational wave. And I again emphasize this is a very important thing to realize, that these imprints on the pulse timings have very high degree of fidelity. So signal transmission from pulsar detector to Earth has very high quality. Now, reaching out of extra galactic pulsar will be, of course, very important in this case, because then you may have possibility of some gravitational wave source close to the pulsar. So this is the picture. This is our galaxy. Let's say, of course, we can't picture our galaxy. Something like a spiral galaxy. If it was our galaxy, sun will be here. Sorry, just a minute. Okay. Yeah. So sun will be somewhere here. It's in the spiral arm, and this is where you'll be detecting it. And our galaxy has a lot of globular clusters. Globular clusters are very dense clusters of stars and are supposed to be heavily populated by neutron stars. In fact, and pulsars. In fact, amongst all the known pulsars, roughly more than 2,800 pulsars, which are known in our galaxy, More than half of the pulsars are in globular clusters. 100,000 stars in a very compact system of several hundred light years only. So this is the thing. So suppose there is a gravitational wave source like a binary pulsar or something, neutron star merger, and there is a pulsar detector also there. So there is a gravitational wave emitted there, pulsar detector measures here, and you observe that pulsar on Earth here. So you have, so imagine this, all these globular clusters become your, so this, all these globular clusters will have pulsars. These pulsars are now your pulsar detectors. These are the analogs of LIGO Virgo. No? So these pulsar detectors are now spread around whole galaxy. They are connected to you. How? There are no wires there. They are connected to you by their pulses. You sit on radio telescope observatory, you measure these pulsars, and you detect their pulses, and you look for the imprints of the signal, just like people look for the signal coming from the piezo crystal. Of course, a fantastic system will be binary neutron star, which has provided gravitational wave source and detector system. So imagine, I mean, I already, in the first part, I told you that neutron star undergoing phase transition may emit gravitational waves. Now suppose that neutron star is in a binary system with another pulsar, which you are measuring. So neutron star emits gravitational waves, either by phase transition we have proposed, or by something, structural deformation, whatever. And the pulsar detects it. And this system will be very close to each other. This is, I mean, the binary pulsar which I told you, Hall's stellar, is 1,000,000 kilometers separated only. 1,000,000 kilometers. It's few light minutes. Forget about light year itself. I would argue 100 light years, 1,000 light years for a few light minutes. So the gravitational wave strain will be very large on that. And the pulse timing will be affected very strongly. So this kind of binary neutron system can become a fantastic system for the pulsar detection as a Weber detector. Now this is the last part, and this I find most exciting. You see, I mean, this is just the problem moves by itself. We started with QCD, it went in direction of emission of gravitational waves, then we look for external gravitational wave. Now it becomes very obvious what we have to say here, that this is the thing. Gravitational wave already reached us, suppose. Gravitational already reached us. So there is far away gravitational source at the sun, and gravitational wave reached us directly. But the same gravitational wave reached pulsars also. So maybe I should show this picture first, then I'll go back to that picture. This is a gravitational wave source. This is Earth. And we detected gravitational wave, suppose, by LIGO Virgo. We detected it. But the same gravitational wave was emitted, which was emitted to us, it also went to some pulsar. Pulsar got affected. Its modified perturbed pulse will reach us on Earth. Now, everything going by speed of light, A plus B path is always bigger than C. Always bigger than C. That means that modified pulsar timing will reach later. And of course, it's obvious that once you know the astronomical coordinates of pulsar and this, you know the time difference between A plus B path and C path. You can exactly predict it. If I know when the gravitational wave source reached on Earth, if I know that time, I can predict in future when pulsar modified signal will come to us by which pulsar. So that's what it is. So you come back here. Now this is Earth sitting here near sun. Some external source comes. This source emits gravitational wave which we detected directly. It went to different pulsars. Different pulsars will get their pulse modified, and those signals will keep coming at different times. Very well defined, calculable, predictable timings. They'll come to us. And we can sit and predict, and in future we can detect those sources again. But even more exciting, suppose the signal came in past, which there was no LIGO Virgo at that time. Signal went through in past. We missed it. Some examples are supernova events. Supernova, we have astronomical records. Supernova also emits gravitational wave. One knows how much is the amplitude typically, and can estimate that. We know the dates of supernova because they were observed. We know the dates of those supernova, and we know the location of supernova. So because of that, we can predict those events of supernova for which there is no signal of gravitational wave. It will get imprinted on pulsar, and we can predict that in future. This is the work we have just published now. And let me tell you, So let me not worry about the equation here. So this gives you a remarkable possibility of revisiting the past gravitational wave events. And if it works, it will be very important. It will give you ability to look at events which occurred in far past. You will, I'll tell you some of the very exciting cases. Supernova 185 AD. There is a record, astronomical record. You have chance of looking at that direct live signal now through a pulsar. Okay. More importantly, you can get the same signal through different pulsars repeatedly. It's not just once in the time signal. From one pulsar it comes now, from one pulsar it comes after 20 years, one pulsar after 70 years, another pulsar. So same signal coming through different pulsars. Of course, different pulsars have different interiors, so it will be modified differently. And their angles are different, so modification will be different, but the same source. So you can really study properties of that signal thoroughly by different detectors. Of course, the important thing is you can also detect any circularly polarized component of gravitational wave, because it directly affects rotation in this case. So now let me tell you some interesting events cases. So what we did is, we went through the whole catalog of gravitational wave sources which have been measured, and all the past recorded supernova events, astronomical record. We went through that. Those become our gravitational wave sources. Then we went through the table of all known pulsars. And after this, all trigonometry. Just trigonometry. We know when the direct signal came on Earth, when they were observed, say supernova was observed optically. This is important thing, optical signal comes little later than the gravitational wave signal would come, but it's not that much different. So you'll see the error is quite a lot in our case. In any case. So there's a black hole merger, which was detected by LIGO Virgo 170814. That event will come. This event will come to us via pulsar. This particular pulsar from 2035 to 2043. That's a prediction. Of course, given the mean value of coordinate, this takes care of the errors. Given the exact coordinates which are given, we find out the minimum time which is there. Minimum time we give you exact value. 7 August. This is 7th August 2035. Actually, it is one should not take it very seriously the exact date, because you see the error is large here. 2035 2043. 8 years. But the reason I mentioned date here is that the error is coming because of errors in the coordinates, astronomical coordinates only, nothing else than that. If astronomical coordinates can be improved, this date can be pinned down very accurately. And as I said, past supernova events, of course, in this case, all errors are not known. Pulsar distance errors are very difficult to know. That was not known very accurately in this case. So but there are a couple of cases where all errors are known. So for example, supernova 1604. Supernova in the 17th century, 1604, there is a record of that. That obviously we have missed. We don't know what happened to the gravitational wave. Via this particular pulsar, this is the time from 1971 to 2052. We have calculated and presented the numbers only for those cases which are from 1967 onwards up to 100 years. Because 1967 was around the time when pulsars started getting recorded. So we have a past data for pulsars. So idea is that what our proposal is that one should go to the past record of pulsar data and look for these signals, very, very well-defined signals of the gravitational wave. Look for these signals, and future, if they say, you should just measure the pulsar very accurately. These are some of the cases for which we know all the errors. Not many cases, only 4 events we know, which are all the errors are known in this case. CRAB pulsar, it's such a famous pulsar. CRAB pulsar is from 1994, but of course 2021-84. This looks too far away in future, but can come anytime. But the important thing I say is 1604, SN 1604 from 7152, SN 1885. SN via this pulsar will come between 2022 2044. This we consider a gold signal. 2022 2044, 20 years of time, but during this time it will come. There's no question about this signal. This signal will come, you keep monitoring it, and you will detect this SN 1885 supernova by live signal. And this gravitational wave source which event which have been retrieved by LIGO and Virgo between 2024 to of course this future is, because this in this case gravitational wave source was very poorly known. Its coordinates were very poorly known. So of course then we have a whole table. So earliest known supernova, CAPSS, pulsar, all those things we have given the whole table. In our paper all these things are there. So how far back in past can we go? How far back? Our galaxy is 100,000 light years across. So clearly 200,000 years from one edge. So say gravitational wave source being close to us, 100,000 years ago, it emitted a signal which went to a pulsar which is on the other side of the galaxy. We obviously missed the signal. 100,000 years ago, there was nothing here. That pulsar sent its signal. It takes 100,000 years to reach us. So 200,000 years. So that is the time 200,000 years ago signal can be measured. 200,000 years old gravitational wave signal, we have chance of observing live in future. That's the strength of the signal. Important thing is, several important points here. One thing is very important to know about the pulsars in other galaxies, reaching out for extragalactic pulsars. And the most important thing is, for past gravitational wave events recorded on Earth, whatever else, this is the thing which we told our referee, when referee was arguing with us, we told, actually we agree with referee. We said, yeah, sure, we agree that our calculations are crude, we don't know quality factors, we don't know what we signal, but remember, the dates are beyond question. There is no model dependence at all in the dates. Dates is just trigonometry. So dates are correct. Now, if you know that there is going to be a signal in next 10 years on that pulsar, but you don't know whether the pulsar interior is friendly enough to give you the signal, I would say you give it a try. It will be pity. We don't know, a pity not to do anything during the time when we expect the perturbed signal to arrive. Now, I was telling you we don't know the quality factor of neutron star. We expect it to be very high. I'll quote something which we also quote in our paper in response to referee also, and referee accepted it, that this is from a review article. This review article reports in Prof Physics, Lou, Blair and Zhao, detection of gravitational wave. It's about all different kind of detectors, and they had a whole section on resonant mass detector, Weber detector they were talking about. And for the antenna material, this bar antenna or this spherical antenna, they say the following: an ideal resonant bar would consist of a piece of nuclear matter with high density and a velocity of sound comparable to velocity of light. Since this is not available except in neutron stars, we must find a form of molecular matter which, to maximize coupling to gravitational waves, combines high velocity of sound and high density, and to give high Q factor, like aluminium, copper and all that. Because the ideal thing is available only neutron stars. And what we have demonstrated in our paper is that neutron star indeed is ideal, and actually it can work as a Weber detector, and we simply have to monitor it by monitoring its pulses. Okay, I'll stop here. Thank you.
Thank you, sir. It was an amazing talk. I'm sure everyone has enjoyed it, and the topic was really interesting. So now the talk is open for discussion and questions. So we will take up a few questions from the audience. So does anyone have any question? You may please raise your hand.
I have a question. So, hello, sir.
Yeah, sure.
So, is there any way of detecting if the gravitational wave is coming from the density fluctuation within the pulsar or the outside? It's coming from some outside source. How to, differentiate between these two, or is it at all necessary?
Yeah, sure. No, it will be completely different actually. When it's coming from a phase transition inside the pulsar, it will be a random component. So it will be random component will have a random change in moment of inertia and wobbling also. Whereas a external gravitational wave will have a very specific form of the signal. In my first slide was about the template, you remember? Template. That you should know what you are trying to do. LIGO and Virgo, how they detect the signal is, they know they are trying to detect coalescence of object. So this coalescence of object, they know the time. I think there's a background noise. So they know So they have this template where there is a signal form is known. So that form of the signal you superimpose on the signal which you have observed, and you fold it several times. So that's what you have to do there also. If you get some kind of noise, some kind of signal on from pulsar timing, then you have to try different options. Try black hole merger, try neutron star merger, try supernova burst. Okay, all those things you try. Try even a pulsar interior. Signal to noise ratio will be maximum for only one kind, and that will be the correct signal. That's the template. So that's how the LIGO work out with. That's what you'll have to do here also.
Okay. So we already have the templates for like if it's coming from the density fluctuation or it's from the neutron star mergers and so on.
We have for all other cases except for density fluctuation. Density fluctuation is only our proposal.
And it's
so we are actually working. This is one of the projects we are doing right now to produce a template for density fluctuation.
Okay.
This is one of our projects right now.
Okay. Thank you, sir.
For all the cases, you know the template.
Okay. Thank you.
Thank you for asking question. I would request if anyone has any question, please introduce yourself first and then you can ask question. So we have another question from the chat box. This is Shayok Chatterjee. He asks how to disentangle the perturbation in the signal coming from pulsars due to gravitational wave and say due to some other source. I mean, do we know all the possible backgrounds to the exact proper signal extract the proper signal?
No, we don't. So that's why one has to look for. In fact, we had a whole section in our paper about the nature of the signal. So you will need to know pulsar timings are known very accurately, and all the perturbations are which have been measured fall in different categories. So, for example, the glitches are known. Glitches are there. So, in fact, this was the referee also had asked us, how would you separate your signal from glitches? So, the glitches arise in a very specific manner. The rotation suddenly changes, increases, but then relaxes very slowly over a period of months, only to 50% of the original rotation. What happens in this case, gravitational wave is a transient phenomena. So, once it goes through and it gets absorbed, then its rotation will change. It will keep ringing for some time to the ringing effect. It will lead to probably millisecond pulse will get enhanced to few minutes or maybe a few hours. No way it can extend to few days even, forget about few months. So that means after few hours, it will completely restore the original signal. So gravitational wave signal is very, very specific. It will represent something came and passed through the neutron star. Some wave came and passed through the neutron star, which was transient only. Didn't induce any permanent changes. So no other thing will do that. Nothing else will do something like that. Everything will deform in a regular manner, in a permanent manner, like glitches. Not permanent manner, for long-lasting time. Does it address your? Do you agree with what I'm saying? Okay.
Shayok, if you're online, you can talk directly with sir. He says, okay, sir. Thank you.
Okay, fine, sure.
In the chat box.
Okay.
Okay, so are there any other questions from the audience?
Yes, I would like to ask one question.
Yes, sure. Pratik, you can. Okay, we know you are Pratik. You can.
So my question is that from the characteristics of the pulsar signals, can we detect the location of the gravitational wave source?
That's a very important point. We have said in our paper. You see, this is in one case, pulsar detector is a very rich detector. With LIGO, if you have a single detector, that's why LIGO Virgo 2 are needed to get some idea of the original direction. Even then, you know that you have a very poor constraint on the angular coverage of angular location of the source, because that's the nature of detector. Now, in this case, pulsar, the gravitational wave is coming from some direction, induces quadrupolar deformation in the plane perpendicular to the gravitational wave, and depends how that plane is aligned to the rotation axis of the pulsar. Depending on that, the pulse will be modified. So it's not just knowing about the original template. You also have to, that's a very complex calculation, numerical simulation one has to do. This also is one of the projects we are doing, that take the original template coming from some arbitrary angle and produce what kind of change will happen. It will depend on the angle between rotation axis and the direction from this is coming. Of course, there will be still degeneracy. Always, azimuthal angle will remain degenerate. But other than that, you will know the source. So there are three things now: the source direction, pulsar angle between them, and the pulsar direction to you. Given that, you will be able to narrow down the source direction to very high degree, even with single pulsar time. Exactly how much that we don't know, that we'll have to work out simulation.
Okay. Thank you, sir.
Yeah.
So, are there any other questions? Maybe from YouTube or Facebook? Is there any other question? I think no.
Okay.
Okay, so in that case, we may close today's event, and thank you,
Is the
sir,
question
once
here?
again.
There is a question in the chat box.
There was a
Okay,
question
there
in
is
chat.
another question. Okay, there is another question. It's from Orko Prabhu Ghoshal. He asks, if two sources make some kind of superposition, how to detect what is the actual source?
That we don't know. That we should not know, because first of all, it is extraordinarily unlikely, because you see the pulse timing will have to be matching within milliseconds. Even the ringing, the beginning happens at millisecond level, right? So two pulse timings will have, two sources will have to strike the pulsar within the short time. This is very unlikely. Gravitational wave sources are common, but not that common. So, but if it does happen that two sources strike the same pulsar around same time, clearly if you try to put the template of one, it won't match. So maybe then one will have to try template of two. It is going to be messy, I suppose. I wouldn't know how to. Yeah, how much one can disentangle, I would not know that.
Okay, there is one question from YouTube. It is by Anand Dubey from VCC.
Okay.
He asks, on what factors does the required sensitivity of the detectors depend?
In our case, it's the Q factor. Simply nothing more than that. The pulsar timings are already accurate enough. 1 part is 10^15. That's the phenomenal accuracy we have already achieved. Of course, one could try to improve that also, but that is already, people are doing their best in that case anyway. So the only thing which remains now is that what is the Q quality factor of neutron star interior? And that's also not in your control. You should simply calculate some QCD calculations. And that is a very important calculation which one needs to do. And this is what we have been campaigning for, that the QCD community has to realize that this number is a new number. It's not viscosity only, not equation of state, something different now, involving all these things. And that quality factor can play instrumental role in Weber detector. And I'm sure 10^6 of aluminum bar will be nothing compared to what we get. If we can get quality factor of 1 billion or more, then I would not rule out the possibility. I should not appear too optimistic that Weber detectors, pulsar Weber detectors, might compete or even exceed the sensitivity of LIGO Weber, because there is no limit to it. Then if you can have ringing effects lasting for very, very long time, you might compete competitively.
So Anand sir has put another question.
Okay.
He's saying, how strong would be the signal source?
How strong would be the signal source? Okay, let me understand. Signal, there is a source, gravitational wave source, which has some gravitational wave strain at the location of neutron star. That's a different thing, no? So whatever I told you that if the h is the gravitational wave strain at the neutron star h, then the delta nu over nu, fractional change in rotation frequency is 10⁻² times h. Okay, so that's what it is. I mean, but this is just a raw number. But ringing effect is different. As I'm saying, delta nu over. So suppose it's 10⁻21 there. Suppose the h is 10⁻21, like you get on Earth. Then delta nu over nu will be 10⁻23. And I said you have delta nu over nu of 10⁻15 measured by pulsar. It looks hopeless, right? In that case, I would say not really. Even if such weak gravitational wave source is, if the neutron star Q factor is say billion or trillion. I don't know. I mean, I actually don't know. I shouldn't say the number because I have no idea. Then even that is accessible. Even that might be accessible. But you see, the beauty of the pulsar detector is this: that it's not on Earth. It's spread around in the galaxy. So you should look for a pulsar detector which is close to gravitational wave source. That's it. And hopefully it will have a much higher value of gravitational wave strain on the pulsar than what you're getting on Earth. And does it address, Anand, your question, or you? Maybe I didn't get exactly what you're asking.
Actually, Anand sir is asking this question from the YouTube.
Okay, right. So
He also has sent a message that thank you for such
Okay.
a nice talk, sir.
okay, sure.
Sir,
Yes, Pratik.
sir, may I ask a non-technical question now?
Yeah, of course, sure.
Since we know that you are such a good speaker, so I would like to ask you that what is your view on research methodology, so that we the young researchers can gain some insight from you.
Um, it's a difficult. It's a research methodology gets very tied up with your view of life itself. You know, how do you view your life? How you view the research? Actually, I gave a talk, I think 2 weeks ago, on for CBS students. This is called Science, Learning and Research. Three idiots way. It is on YouTube, where I discuss my views about research and learning. So I think this is a very loaded question. How you look at research, what you are looking for, what rewards you are looking for research. If it is the happiness and pleasure of doing research, then you approach research in a different manner. So for me, this has been the way that I look for the when you said at the introduction, very sweet introduction you gave here about that I work on a variety of things from liquid crystals to gravitational wave. That's because of my attitude towards physics. I don't have any specific agenda in research. I remember a long time ago, somebody was asking me, some very big scientists were asking me, Ajit, what is your main goal in physics? What's your agenda in physics? So I told the person, I don't think I understand the question. I don't have agenda in physics. I love physics. And wherever I find it interesting, I work on that. So for example, as you can see in this problem, we started with QCD, and it led to a direction of gravitational waves. So normally many people would say, okay, gravitational wave, fine. It is not my research area, somebody else's research area. So let me dig deeply in the QCD part of it, which is a very good way of doing it. Then you can dig deeper in the QCD signal of pulsar. For me, there's nothing, no stopping such barriers. It leads to gravitational wave. Let me learn about gravitational wave. So I just crossed the barrier. I started learning gravitational wave with my students. We started learning about gravitational wave. We learned about gravitational wave, pulsar details, and all those things. We went in that direction. We learned it. This is exactly how. So same thing. My liquid crystal research. If there is a border to be crossed, of course, it is an extreme border which is very difficult to learn, very very difficult. Then I will not do. I have not done it. In many such borders, I have backed off from them. Too difficult for me to learn. But if I can manage it to learn, I go in that direction. It should be just interesting physics. If it's interesting physics and problem excites me, I will work on it. That is my research methodology in nut and shell. Do you want me to say something more, Pratik, or this is good enough answer for you?
No, it's good enough. Actually, what we face is that, like, someone is doing a research on an X field, suppose.
Yes,
and,
right.
And in his research, he faces a question from Y field.
Right.
Now, it is very difficult for him to approach that question without having sufficient background knowledge or someone to talk to about who is an expert from that field.
Right.
So many times it happens that even if the person is interested or excited about that question, due to the lack of communications or actual technique to attack the question, so the person may lose interest. So
Yeah, I agree. I mean, if it is, sorry, you are completing, huh?
no,
Complete.
no, no. Yes.
That's enough. So yeah,
Yeah.
I mean, I agree. So if you're, I mean, if you have to, so you have to see what is the thing is required of the different field. If it is a very deep things of that field required, which requires a very large commitment from your side, then there's a practical difficulty in doing it. But often, quite often, it's not true. Quite often, you see, you don't need experts to teach you field anymore. We learn all the gravitational wave we have to learn from internet, from YouTube lectures and to books and to lectures through introductory lectures. So you can learn anything these days from internet. It just requires extra time. Main thing is you should not have any mental barrier. This is a different area from mine, and I cannot get into it. It's not true. Most of the other areas you can get into it to some level, but if you make an effort, if it becomes very, very hard and it's compromising your original work, then don't do it. But no, for a lot of things, you will see that it's not that difficult actually.
Thank you, sir.
Okay.
Okay, so I think that was the last question from the audience. If there are any other questions, you can ask anyone, or else we will close today's event. Okay, sir. So thank you once again
Thank you very
for
much. I enjoyed
finding
it.
time to give this lecture. We all really enjoyed it.
Welcome. Yeah, I enjoyed
Thank you.
myself very
Yeah.
much. Thank you very much. Okay, so I'll stop with it. Bye bye, everybody.
Yes, sir.
Bye.
Bye, sir.
Bye.
Sir. Bye, sir.
Okay, thank you all. We will meet again next week. Bye. Thank you.